Hello everyone. So this is a part two of my lecture on February 19th. Actually, in the part one, we solved all the questions except this question number 27. So this question number 27 is what we are going to work out now. But just a recap. So we have the circuit like this: three impedances Z1, Z2, Z3 in parallel to a voltage source, 220 angle 30, voltage of 40 hertz. So we already, if you did not see the part one of this video, please go to the part one video. Maybe I will give a link separately. Uh, Meanwhile, now I will show the code that we had written to solve the other parts of the question. So here, okay. So I think I have to open the, just a minute. So this is a code that we already discussed in the part one of this video. So I will not again repeat everything except that Z1, Z2, Z3 are mentioned here. Total impedance, all these things, they're all calculated. So now the question number 27, separate video is needed because it is the most trickiest question. So let's see what it is. The question is, by placing an inductor or capacitor across the voltage supply, the power factor of the circuit becomes 1.0. Determine the value of the inductor or the capacitor. So across means connection in parallel across the voltage supply. That means connection in parallel to the voltage supply. So what I am doing then is there is this three voltage Z1, Z2, Z3 and a voltage. So now there will be a fourth branch. That one either capacitor or inductor. That fourth branch will make the power factor of the entire circuit one. That means it will cancel out all the reactive power in the circuit. To explain further, I just made some slides on this. So just have a look at this. So by placing the inductor or capacitor across the voltage supply, the power factor of the circuit becomes 1.0. Determine the value of the inductor or capacitor. But first, let us see whether it is inductor or capacitor. So what we did already, we had Z1, Z2, Z3. These three in parallel are there with a voltage source. We converted that equivalent into a ZT. That means the total impedance we already calculated. That is 8 plus J 13.48. So now if I go to the results of my code, so here you can see in this line Z1, Z2, Z3 are there, and then the total impedance ZT is there here, 13.4831. So uh, now these two circuits are equivalent. Now because this 13.48 reactive impedance is there, it is taking the reactive power. Now I want to cancel this 13.48. Now that there are two ways possible. This one. Now look at this. To make the power factor 1.0, either I can add a capacitor in series or I can add a capacitor in parallel. Both are possible. So here, why I am saying capacitor, why not inductor? Because the inductance J plus 13. Because this is already inductance is there. To cancel that inductance, I can add a capacitance. But if I add this capacitance in series, then the value is known: 13.48 positive, 13.48 negative, both will cancel out each other. But this is not asked in the question. In the question, what is asked is, I want to connect a capacitor in parallel with the or across the voltage so that the total impedance becomes uh, purely resistive. Okay, so this part is what we need to calculate. So here slightly it is more complicated. So to make it simple, what I can do is that I want to make the active power supplied by the voltage source. Let me explain what that means. You know, the complex power S is nothing but P plus JQ. Active power plus reactive power. P plus JQ is the complex power. Now, individually, S can be calculated by taking the magnitude of voltage and magnitude of total current. Then I'll get the S. And P is already calculated. Individually, P1, P2, P3 we calculated and we already got the P. Now S and P are calculated. Then I can find the Q by this right angle triangle. So S square minus P square under root will give me the value of the reactive power Q. So what we are now saying is look at this circuit diagram. The capacitance is in parallel with the voltage source. So the total power received by the impedance is 1576 active power plus J2653 reactive power. We already calculate. Let me show. I'll show the calculations later. Now this J2653 reactive power, if it is supplied by the capacitor, that is cancelled by minus J2653, then only the active power 1576 will come from the voltage source. Therefore, voltage source will become in series with the in the sorry the voltage source will become purely power factor 1. Okay, so from this concept, now QC is known and V is known. So from V and Q, I can find the XC, and from XC I can find the capacitance. So this is the process that we will be following to answer this question. So what is the objective now? First, to find the Q. Okay, so already I have written the code. So let me show you that code. So here, look at the line in which I have highlighted. So P1, P2, P3, all the three powers. Absolute value of current I1 square into 12, absolute value of I2 square into 16. So this is the three powers are calculated, P1, P2, P3. Now what is PT? So look at this line which I am highlighting. Total power PT is nothing but P1 plus P2 plus P3. So I got the total power. And what is the S? S is absolute value of voltage multiplied by absolute value of the total current. That will give me the total S. So now I know total S and total active power. So I can find the reactive power Q. How I can find? Square root of S square minus P square, PT square. So then from this I know Q. Okay. So P, S and Q. So let me just show you that one in the results part. So here you can see this line. So the total apparent power is 3086 volt amperes, whereas 1576 is the active part of it and 2653 is the reactive part of it. So these two are 90 degrees with each other, and this is the kind of right angle triangle. So now I got this 2653. Now let me go back to the diagram. So here you can see 2653 is the reactive power consumed by the total impedance, and the active power is 1576. This 1576 still comes from the voltage only. But the 2653 I want to cancel out locally by keeping a capacitor. Okay. So therefore, from the V and Q, I can find the C. So V square by Q is XC. So that is another formula. So I go here, and then here you can see the line in which I am highlighting. So absolute value of V square divided by Q will give me the capacitance XC. Then from that XC I can find so it is actually 1 divided by 2 pi f. F is 40 and XC. But because I want in microfarads, I will add a 10 to the power of 6 in the numerator. So the answer will directly come in the microfarads. Now these two lines you ignore. So I'm interested in the value of XC and C. Okay, so let us run this program and check again. So here the C and XC values are there. So the reactance is 18.24 reactance, the capacitive reactance, and the capacitance value is 218.124. And if you're worried about plus minus sign, need not worry, because we know that it's a capacitance and it should be that. So 218.124 microfarad is the answer for question number 27. So let me show you that choices. So here question number 27. So 218.1 microfarad. This is the A is the correct answer. But there is another answer C, 295.1. Okay. Now what if some student assumes it as a series? Okay. So now if I go back here to this slide, to make the power factor 1.0, I can connect the capacitor in parallel like this second circuit, or I can connect the capacitor in series also. If I connect the capacitor in series, what happens? I will take the imaginary component of the impedance, whatever 13.48, and I will take a minus sign, and that one will become the reactance of the capacitor. And from that reactance, I will calculate the capacitance. Okay, so let me show that here in the code. So here you see this line where I am highlighting the ZT, the total impedance, then the imaginary part I am taking. That imaginary part I am assuming that XC wrong. HC underscore W means HC wrong. So by mistake, if I do like that, and then I calculate the C with the same formula using XCW here, I will get a wrong value of the uh, capacitance. So that one is printed also. So already here you can see in the answer. So the XCW in this one. So the wrong value of the capacitance is 295.1. So to mislead the student, so that also is given as one of the choices here, 295.1. So the C, sometimes student may calculate and get the answer, but C is the wrong answer. It's a misleading answer. So the answer is A. So I hope you understood this question. This is the most. This was the only complicated question in the whole thing. So you just try to understand these things, and with that, I solved all the questions pertaining to one part in this exam. That is like from question number 21, I solved up to question number 30. Then we have another circuit and all, so we can simply change the same code. See what I will do, simple hint I will give you. Z1, Z2, Z3 are there, different values are given here, but how do you find the total impedance here? Z2, Z3. So if I were to solve this circuit, so I simply have to say here how to find the ZT. So ZT will be Z1 plus 1 divided by 1 by Z2 plus 1 by Z3. So what this will do, here 2 and 3 are in parallel. That whole thing is in series with 1. So that way it will give a total impedance of something different. So and then the rest of the calculations will be similar. And of course, wherever changes are needed, you need to properly make that change. Just with that hint, I will end this video. So you all have the question paper. So please solve the other questions also in this exam. So thank you so much for today's class.